Hi, and welcome to this tutorial on Python. Today we're going to be covering some Python basics. Generally speaking, numbers, using Python as a calculator. And we'll also introduce the concept of functions to save and reuse some of our logic, our step-by-step processes. In the previous tutorial, we talked about how to download and install Python. So if you haven't gotten to that point yet, go ahead and check it out. We're going to be entering code into the Python interactive terminal. You can use the regular Python terminal, the IPython terminal, which is a little more advanced, it's got some extra features, or do what I'm going to do, use a Jupyter Notebook, which allows you to nicely document what you've learned. So let's go ahead and boot up our Jupyter Notebook. If you followed along from the previous tutorial and installed with Anaconda, Jupyter and IPython are already installed. If you haven't, you can install them for free with pip install Jupyter or pip install IPython, and that'll get you up to speed. You can launch Jupyter Notebook from the command line by typing Jupyter Notebook. Clicking this link here will launch your browser. Once Jupyter Notebook is up and running, come over here and click this new button from the drop-down menu. Click Python 3, and this will launch an instance of the Python interactive interpreter in our notebook form. We can rename our notebook. In this case, I'm going to title it the title of this tutorial, Python Basics, Numbers and Functions. There we go, we've got it renamed. Let's go ahead and start entering some code. First, a little tip. You can type anything after the hash sign becomes a comment and is not executed as code. Anything below or anything not commented is considered code. Here we can do 5 plus 10, a simple addition problem. And there we go. We see we have an input block, right, in line number 1 and out line number 1, which gives us a result of 15. Checks out. Let's go ahead and do a few more. Subtraction, multiplication, division. So notice the difference in that last line, output number 4. We've got 10.0, so we got that extra decimal on there. And so this is telling us that division is returning what's called a float in Python, or a floating point number. So it's going to have this decimal property instead of a whole number, like in the previous outputs, which we're calling an integer. So that those integers will not have any decimal notation. There is a separate division operation called floor division with the double backslashes or forward slashes, excuse me. And this is always going to return the whole number portion of any division operation. We can also do exponentials. 5 squared is 25. This uses the double star instead of, you might see a caret in other languages. In this case, we are using double star notation. So similar to how you can just get the whole number part of a division operation with floor division, we can use what's called the modulo operator, the percent sign, and calculate just the remainder of a division operation. This is all well and good, but what if we want a little more complex expressions? Well, we can use parentheses to group our expressions and control the order of operations. Right? Here's an even more complex expression. Well, that's fantastic. We are entering Python code into the interactive terminal. But so far, it's just been any old stuff you can do in a calculator. But maybe you're asking, hey Dan, is there a way to store the result of my important calculations so I can use them later? And the answer is yes. You can use variables to do that. You can think of variables as containers to store a value that you can then reuse later or multiple times. Let's go see an example. Okay, so let's take a look at how to assign values to variables. Here we have the value 2 assigned, which is what the single equals sign operator means, to the variable which we named x. Now, there is a second operator with the double equal sign for equality, but we'll get into that when we talk about logical comparators in a later tutorial. Now that we have the value 2 assigned to x, we can use x in place of 2 in future code. For instance, if we have x plus 3, we'll get 5. We can use this multiple times. X plus x plus x gives us 6. You get the idea. Alright, so we've seen how to assign a value to a variable. But thus far we've only used x, which isn't very descriptive of what the variable does. You can name variables anything you want, with a couple exceptions. Here are some examples of good variable names. Typically, they have to start with a letter. They can be capital, lowercase, it doesn't matter. You can also begin a variable with an underscore, in the case of this moose. Sometimes that means you want this variable to be private, but that's a detail for a later time. Here's an example of some variables that won't work. You can't have spaces in your variables. You can't have quotes, special symbols like spaces, quotes. You can't begin variables with numbers, so this also won't work. A good practice is to make your variable names descriptive. Here's an example where we store our fairly complex expression in a variable called myImportantResult, which we can then use later on in the code. So you can reassign variables to new values. In this case, myImportantResult is 200. And then when you reuse this, it will have the new value instead of the old value. Nice. Well, that wasn't so bad. We learned how to store the results of our complicated expressions in variables so that we can reuse them later and multiple times. We got an idea of how we can name variables so that they're more descriptive and it's easier for us to read. But hey Dan, what if I want to store some complex logic and reuse it instead of having to type out these expressions all the time? It's a great question. And we can use functions to accomplish this. So functions are similar to how variables can store values for later use. Functions can store logic or a sequence of steps for later use. Let's look at how we can define our own function. We can use the def keyword. We give it a name, in this case save my logic, and we use these parentheses. This is part of the function signature, and we end with a colon. When we hit enter, you'll see that it indents here. And then we can type return 2 times 8. So this function called SaveMyLogic is going to return the value of 2 times 8. All right, we execute that code block. And what happens is it saves this function in the name SaveMyLogic, similar to how a variable. So we can call this function by typing SaveMyLogic and using the parentheses. So now we see that it returns the expected value, 16. Notice this return keyword. If we add some extra, let's redefine our SaveMyLogic function. In this case, let's add some extra steps. We're going to say x equals 3 and y equals 4. And then when we use the return keyword, this tells us exactly what we get back. You can have any number of steps in a function. Here we go, 12. You can reuse your function as many times as you want, and you can store the results of your functions in new variables you define. Here we go, new variable, SaveMyLogic times SaveMyLogic plus SaveMyLogic. You can see we have to use the parentheses to call the function each time. And the value of our new variable is 156. Let's update our function again. In this case, we're going to add this line here in these triple quotes. This is called a docstring, and this is a little bit of documentation that helps tell us and other people who use our code what this function does. We can use the help command and the name of our function to display the docstring. Help is a built-in function in Python that you can use. You can even call help on the help function. I want to point out something here. When we called help on our SaveMyLogic function, we did not add the double parentheses here, right? Because we're not calling our save my logic function. We're not executing the code and trying to return the value of 12. We're passing the function itself to the help function, right? So within the parentheses here, we're passing a value to the help function. So next you're asking, can I add these values to my own function? And the answer is yes. So let's update our function once again. Instead of saying x equals 3 and y equals 4 specifically inside the function, let's add what are called parameters to our function, x and y, here in the function definition at the top, right? Then we can remove x and y from our code. We can update our documentation to say multiplies by x and y. And there we go. That is our new function definition. X and y are called parameters. When we call our function, save my logic, the values we pass into x and y are called our arguments. So 4 and 5 are the arguments, and then x and y are the parameters. We can store values in variables, whatever we want, right? Cats equals 5, dogs equals 10. Then we can call save my logic, and we can pass in cats and and dogs. There you go. And the values are passed into our function, and we get the expected result. Now the order in which we pass arguments into our function is important. It follows the order in which we defined it. We defined x and then y. So if we get confused, we can use the help shortcut question mark in IPython and Jupyter Notebook, which will give us the doc string, right? Multiplies x by y. This is what we defined earlier. And it also gives us the function signature, which will tell us the order of the parameters we defined. So that's pretty handy. All right, so now we're getting somewhere. We've defined our own function, a set of logic and reusable code that we can use over and over again. We learned how to assign values to variables. We learned how to return the output of a function and store it in a variable. But thus far, we've just been sort of randomly adding and multiplying things together. How about a real-world example involving some finance? Everybody likes money, right? Let's take a look. Okay, so let's take a look at a real-world example. In this case, we're going to take a look at calculating compound interest of an investment. So here we have the amount in A, the principal, 1 plus the annual interest rate over the number of, let's see here, periods. Excuse me. So right off the bat, we can make this a little more readable by giving our variables more descriptive names. Excuse me. This is LaTeX, by the way. This is a way of writing mathematical notations in an easy to read form. That's something that you can look up if you want, but it's just for documentation here. It's not actually Python code. So here we go. So account total is the principal, 1 plus over the interest rate, the number of times it's compounded per year, and then to the number of times compounded per year times the number of years. So how can we then take this function and write it, this equation and write it as a Python function? So let's say, we're going to say define a function. We're going to call it show me the monies, right? And then we're going to define our function parameters. So we have the principal. We have an interest rate. We have the number of times compounded per year. And then we also have another variable, the number of years, right? So we have our colon. We hit return. We see it's indented. So we can continue. We can define our docstring, calculate the total account balance of an investment. Documentation is important. This helps us understand both other people's code when they write documentation, and it helps us understand our own code when we come back to it, 3, 6 months, or a year later. All right, so how are we going to write this function? We can say the account total is equal to the principal, right, times, here's our parentheses for order of operations, so the interest rate divided by the number of times compounded per year. Okay, and then to the exponential of the number of times compounded per year times the number of years. Great. And then we want to return the account total. So there we go. We've defined this function. So let's go ahead and say, let's define some values now. Yeah? So let's define principal. Let's say it's $500, and our interest rate is expressed as a decimal. We're going to say 5%, and the number of times compounded per year is just going to say once. Let's say it's compounded annually. We're going to say the number of years in our first example is just going to be one year. So we define these variables. Now in this case, we've called these variables the same name as our parameters, but this doesn't have to be the case. You can name these variables whatever you want. And then when we call our function, we pass them in the same order. So if we hit, if we use our question mark for our help shortcut, it will show us the docstring, and then it will show us the order in which these parameters are called. So we can say show me the monies. We're going to say principal interest rate, number of times compounded per year, and then our number of years. All right, so when we execute that, we should get 525, which is great. So this is 5% per year, 1 year compounded once. But the power of functions is that we can reuse this and very quickly. So let's say I want to find out how much does this change if the number of times compounded per year is monthly instead of annually. So number times compounded per year. So we're reassigning this variable, number of times compounded per year, to the value 12. And then we call our function once more. Let's see here. Let's just copy and paste this function call. And now we quickly redid our calculation, and we see that it changed, but not so much. All right, what else can we try? We can see what happens if, oh, by the way, let's make sure that we sanity check our calculation. Yeah, so 5% of 500. Our function seems to be working as we expect. Okay, so let's say we want to try some other things. Let's say, what happens if we change the number of years? What happens if our investment changes to 2 years? And then we can call show me the monies once more. All right, so now what happens if all this goes to 3 years? Right, so now we're quickly iterating, we're quickly reusing our saved logic in our function to try a bunch of different values. So this is the power of programming. This is the power of writing functions. Fantastic, we're moving right along. We've got a real world example with a real financial equation that gives us some interesting information back in the amount of our account balance, which is great to know. We can reuse it very quickly to try and experiment with different values and get a sense of how it works. That's the power of functions. But so far, everything's been multiplication and addition, very simple mathematical things. What if, Dan, I want to take my Uber Python calculator and do some really fancy math? Well, I have a solution for you. We can import additional tools to enhance the functionality of our code. Let's take a look. Okay, here we are back in our Jupyter Notebook, and we're going to take a look at importing an additional set of tools, or a library. You might also hear it referred to as a package. So let's import the math library. So what did that do? That brought in the math library, which is a package of additional tools that we can use to do more complex math operations. This is built in to Python. There are many built-in libraries, but just as we installed Jupyter and IPython with pip, you can use pip to install a bunch of other libraries to enhance your functionality, and you can import them into your programs using this import statement. Pretty simple. So what all is available in the math library? Well, the first thing you could do is go to the documentation for math, right? So this is at python.org. You can then view all the functions and methods in the math library. But perhaps an easier way is to use this dot notation and hit tab, which gives you a list of suggestions of all the methods or functions that are available in this math library. Let's take a look at square root. So math.squareroot calls this square root function that's part of the math library, and we pass it the argument 25. So it's taking the square root of 25. Makes sense with what we've known. So what is this? So square root is a function, but it belongs to this math library or math object. So sometimes you might hear this square root referred to as a method, and a method is just a function that is part of or belongs to an object. And the term object just can mean almost anything in Python could be referred to as an object. It's a very general term. Now there are other things that are not functions in the math library. In this case, there are constants like math.py. You'll notice math.py is not called, it does not have the parentheses. Once again, you can use the help notation. First off, tab. All right, you can then start typing and get narrowed suggestions. In this case, let's see what the sign is, and we can use the question mark shortcut for help, and it will return the sign of x, so measured in radians. So this is very handy. Here's an example. You can take the sine of 90 degrees, but this is in radians, so we need math.py. Math.py over 2 should be 90, and we expect that to be 1. The sine of 90 degrees is 1, so that checks out. Okay, but Dan, you're saying, what if I don't like typing math dot blah 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 all the time, right? That's a pain. I want to save these keystrokes, and I want to be super fast and efficient at typing. Well, there's an answer for you. We can use namespacing. So already, all these functions are namespaced in the math library, but we can do a version of the import statement. So import math as m. So now we can access all these functions and properties in the math library with m instead of math. So m dot square root 25 is also 5. Right. So that's a pretty easy way of doing that. So namespacing is a pretty important concept. For instance, if there was a function called calculate, yeah, and it was in the there was a library you imported, so say blue.calculate. Oops, that's not going to work. And then red.calculate. This is just an example. So by having this namespace, if you had two functions that were named the same thing, this would clearly tell you that you're referring to the calculate function in the blue library as opposed to the calculate function in the red library. And you wouldn't have what's called a collision, right? Then it would be kind of confusing and it would be difficult to troubleshoot bugs. Okay, but Dan, I really don't want to type m.py all the time, right? I just want to type pi. How can we solve this? All right, so you can do what's called a from import and import specifically the functions or properties you desire. So from math, import pi and square root. So now square root is available directly to be called directly. You can also just type pi. See? So this is okay. What this is doing is saying I'm explicitly importing these two pieces, pi and square root, from the math library. So when a user is reading your code or you're reading your own code, you can see that this, where I got these from was the math library. Now there's another format that you could say from math import star. So this is saying from math import everything. So now you would have access to all the functions, including sign, in your local namespace. However, this pattern is not a good practice. This means this is hard to tell like where sign came from or where pi came from. It's also possible that if you're importing multiple libraries, they might have a function that's named something similar, like we talked about with our calculate example. So don't do this. This is not good generally. But the from math or from a library import some specific things you're using, that's very good. So if you don't want to have things typed in a namespace, oops, that's not correct. m.py. If you don't want to have things in the namespace for whatever reason, you can import things specifically into the local namespace. All right, great. We're moving along. So we've been using numbers, and I briefly referred to ones with decimals as floats and ones with the whole numbers as integers. But I think this is a good time to introduce the concept of types. So we've been using integers, but there's a function called the type function, which is a built-in function, so you can use it right away without importing anything. So if we say, what is the type of the number 2? Well, we see that it displays an integer. What is the type of the number 2.0? Okay, this tells us that it is a float. And a float is referred to as a floating point number. It is sometimes called a double in other languages, or a double precision floating point number. But in Python, it's just called a float. Now there are many other types. So if we say, what is the type of save my logic, the function we defined earlier? Well, it's a function, so this makes sense. We can say type math.square root, and we would also expect that to be a function. In this case, it's a built-in function, so it's got a slightly different type. Type math.py. We would expect that to be a float, and it is. Now, when you create variables, you can also check the type of the variable. So in this case, 2 plus 2 returns 4, and 4 is going to be an integer. Now what happens if I add an integer to a float? And then we check the type of x. Okay, so x is now a float. So what happens here is you're adding an integer and you're adding a float. And what Python is doing is automatically converting this integer to a float so that these can be added together. So now x is going to be 4.0. Okay, so this is an implicit type conversion. In a lot of cases, this is fine. This is sort of similar to if you have 10 divided by 2, you get 5.0. So you're implicitly, in some operations, converting these things to floats. So we talked about the implicit or automatic type conversion that is done when you perform some mathematical operations, or that is automatically done on certain operations like division. But you can also manually convert from one type to another. So if you have an integer 2, you can call the float function, which will convert 2 to a float. Now, you can also go the other direction. You can convert your float to an integer. So in this case, this works. However, you should know that if you, let's say x equals the integer of 2.3. So x is 2. So what happened is we lost this decimal information. So if you're converting floats to integers, you lose some information. Just be aware of that. What happens if we try and convert a type that is incompatible? So we had that save my logic function. Can we convert a function to an integer? No. We get what's called a type error. Now this isn't anything scary. It's just saying that in order to convert something to an integer, it's got to be a string or something similar. You can't convert a function. Not too bad. What if we try and add a function to an integer, right? Can we do this? And the answer is no. It can't implicitly convert a function to a compatible type to add the two, right? So it can't add functions in integers. That's what this is saying. Makes sense, doesn't it? Nothing to be terrified about at all. No need to worry. All right, that was pretty fun. We covered a lot of stuff, so let's review what we've done. We basically used Python as a calculator, doing simple math operations with numbers, specifically integers and floats. We learned how to restore the results of our more complicated expressions into variables so we can reuse them later. We learned we can reassign these variables new values as our code goes along. We learned how to store logic, or a series of steps, in functions so that we can also reuse them. We learned how to add parameters to our functions so that we can call that logic with different values. So if we want to iterate, and for example, we want to see like how does our return on investment change as we increase the number of years, change the interest rate, change the number of times it compounds per year. We also looked at how to access documentation on the functions we create and the functions that already exist with the help command and the question mark shortcut. Now that question mark shortcut is available in IPython and Jupyter Notebook. Otherwise, you're using the help command in the original Python interpreter. We learned how to import additional tools like the math library into our code so that we could use more complicated math expressions like square root. We can reference constants like pi. You can also do trigonometric functions like sine, cosine. Logarithms are available in there. You can check out the documentation if you want to learn more about the math library. We also introduced the concept of types, which we've been using types. We've been using integers and floats, but we learned the type function so we can check types, and we learned a couple caveats with how Python sort of converts these types behind the scenes to allow you to add, subtract, and divide, and also ways that we can manually convert these types more. So that's just an introduction to types. Types is a more involved topic that we will just sort of develop over time. So what's next? Well, in the next tutorial, we're going to kind of continue our introduction of basic Python types. So we've covered integers and floats. We're going to look at strings and booleans. And with the concept of booleans, which are true or false values, we're going to introduce these comparator operators. So the double equal sign we saw. We're going to introduce greater than, less than comparators. So we can see if a value is greater than or less than, or if a value equals some other value. And we'll introduce the print function, which kind of goes along with strings. So if you've made it this far, thanks again for sticking around and watching. If you liked this content, go ahead and hit like. If you hated it, hit dislike. If you want to see more, hit subscribe. If you want to see the written version of this tutorial, you can find it at moderncoder.io. So thanks for watching, and I'll see you in the next video. Hey, if you type in import this into the Python terminal, you get to see the Zen of Python. It's worth taking a look at. It's kind of like an Easter egg.